In today's video, we're going to be talking about Newton's first law. After watching this video, you should be able to describe Newton's first law and give some real-life examples of what Newton's first law is explaining. Okay, so let's get right into it. Newton's first law a lot of times is referred to as the law of inertia, and it goes something like this, and you probably have heard this saying before. An object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. Okay, so I kind of think of this as like the law of being lazy. Things in nature don't really like to change what they're currently doing. So if it's an object's at rest, it wants to stay at rest. If an object is in motion, it wants to actually stay in motion. Okay, and the only way to make changes to that is to actually apply an unbalanced force. So what is an object at rest considered? Well, an object at rest has zero velocity. Okay, it's not moving at all. Whereas an object in motion does have a velocity, but it has no acceleration. Because remember, an acceleration is a change in velocity. And to cause an acceleration, you need to apply a force. Okay, without a force, there is no acceleration. So the previous statements are only true as long as they are not acted upon by an unbalanced force. Okay, so as long as there's no outside force acting upon an object, it's going to just sit there. And a great example would be like, set a cup down on your kitchen table. That cup will sit there for the rest of your life as long as no one acts upon that cup. Whether it be wind, whether it be your brother or sister moving it, or whatever the case may be, it will just sit there. It does not want to move. Okay. A good analogy of this is, I don't know if any of you guys have ever experienced this, but here we go. Here comes some of my artwork. This is a car, okay, and it's a really bad looking car. But inside the car, here you are, and let's say you stick your, here's a steering wheel. You stick your coffee on the dashboard. Okay, there's like a dashboard here. And you're driving, and let's say someone in front of you slams on the brake because a squirrel is running in front of, across the road, okay, and they don't want to hit the squirrel. So you have to also stop. What happens to your cup of coffee? Well, according to Newton's first law, that cup of coffee is in motion, and it's going to keep moving unless some force stops it. Well, there really isn't much force here to stop it. I guess the force of friction is in play, but it's not going to be strong enough to stop this cup of coffee. And so what's the cup of coffee going to do? It's going to keep flying forward, and eventually what stops it is your windshield, right? And this is partly why people have to wear seatbelts. Your body is in motion when the car is moving, and if you hit another object and your car suddenly stops, well, your body just keeps on going. Okay, there's nothing to stop your body, and that's the role of the seatbelt. The seatbelt does actually stop your body. It doesn't allow you to move, so it applies a force to your body to stop that motion. Okay, and the same is true as, like, let's say you're at a stoplight and you're sitting there and your cup of coffee's there, and you floor the gas pedal. All right, so you really accelerate quickly off the line. Maybe you're racing someone next to you. The coffee's going to fly backwards because it was at rest and it doesn't want to move, right? But the car starts to move, and so the cup of coffee is still kind of like, in a way, sitting there motionless, and it doesn't want to come with the car. There's no force to help it come with the car, and so it would fly backwards. And that's Newton's first law, basically. It's the law of inertia. Now, this is a huge misconception, okay, and it's something that I too struggle with. It basically means forces do not keep objects moving. Okay? And take a second to think about what that's saying. A force is not necessary to keep an object moving. Okay, so satellites in orbit around the Earth, they basically, it's not like they have an engine pushing them the entire time. Okay, or like an asteroid flying through outer space. There's not like an engine on that asteroid. It just keeps on moving because there is no force to actually stop it. Okay, so Newton's first law of motion declares that a force is not needed to keep an object in motion. So if you slide a book across a table and watch it slide to a rest position, you may say, well, why did it stop? Well, the reason why the book actually stopped is because of the force of friction. Okay, it's not that there wasn't a force to keep pushing it, but it's actually the force of friction that causes that book to stop sliding. Okay, so a force is not required to keep a moving book in motion. It's actually a force that brings it to rest, that makes it stop moving. Okay, so it's kind of, you really have to change your thinking, if you will, for this, because I think there's a lot of people out there who think a force is necessary to keep an object moving, and that is not the case. So what is inertia? Basically, inertia is just the tendency of an object to resist change. Okay, and the tendency for an object to resist change is varies upon its mass. Okay, so mass is the quantity that is solely dependent upon the inertia of an object. So if an object has more inertia, it has more mass, or vice versa. If it has more mass, it will have more inertia. If it has less inertia, it'll have less mass. So mass is the key quantity that inertia is dependent upon. So a more massive object has a greater tendency to resist changes in its state of motion. And a real good example of this would be like, think about trying to get, like a 300-pound box to move. Okay, let's say you're moving a 300-pound box and you're sliding across your kitchen floor. For some reason, you have a 300-pound box in your kitchen floor. And you try to slide it across your kitchen floor. That box is going to resist movement a lot more than, say, a 20-pound box. Okay, and that's what inertia is all about, is basically the tendency of an object to resist changes in its state of motion, whether it's at rest or whether it's moving. I mean, think about trying to stop a moving truck. Okay, that's going to be pretty tough compared to, say, stopping a baseball that's moving. Okay, so those types of things are solely mass dependent. This is a little video clip I wanted to show you guys. I think it's kind of funny. I guess I have a weird sense of humor. But basically, I believe it's at a car show, and there's all these people standing on the stage, and underneath the people there is a checkered carpet. And this cool-looking car comes in, and it quickly slams on its brakes on the carpet and causes the carpet to move. And the people that are standing on the carpet, something happens to them. And we'll kind of talk about that in just a second. So let me show you this video clip.
This is all right. Looks like everybody's okay up here.
So that really is inertia in action. If you watch them, all those guys and gals were standing there and they were not moving. And so they wanted to resist change in their motion. They did not want to start moving. And so the rug moved underneath them, and their bodies did not want to move with the rug. And so they fell. Okay, so that is actually a real good example of inertia in action. Okay. So now we're going to start to head into talking about forces and the difference between a balanced force and an unbalanced force. And I'm just using the example here of, say, a physics book at rest on top of a table. And I'm looking at the two forces that are actually acting upon that book. If you just set a book on a table, I mean, you can do it at home, set any book on any table and look at it. What forces are actually acting upon that book? Well, we know that the Earth's gravitational pull is acting on the book, right? Gravity is always acting on any object on the Earth, so it's always pulling down. So the book is being pulled down by the force of gravity. Okay? The table has to be able to resist that force. If it didn't, the book would just go right through the table. Okay, so it must be resisting that force. It actually must be balancing that force, because if it wasn't balanced, the book would start to move actually. So the book is the table is balancing the force of gravity through something called a normal force. And the normal force is just a force that's always perpendicular to the surface of whatever the object is on. So if you sit on a chair, let's get a chair here, and then here you are. If you're sitting on a chair, gravity is obviously pulling you straight down, and that sometimes is represented by F sub g, force of gravity, is pulling you down, but the chair is balancing the force of gravity through something called the normal force, and that's typically big F sub n, force of the normal. And so that's always perpendicular to whatever it is you're on. The ground, a chair, a table, you name it, that's what the normal force is perpendicular to. So this book that we're looking at in this picture, or now this dude that I drew on a chair, is basically considered balanced, okay? And since it's balanced, there will be no acceleration, there'll be no movement, okay? Now let's say you're on kind of a rickety chair and the chair isn't very stable and you sit on it and the chair breaks, well, you fall down towards the ground, right? Basically, the forces were not balanced. The chair could not balance out the force of gravity, and so it broke and you fell to the ground. Unbalanced forces are basically the forces aren't equaling each other out. So consider pushing a book across a table. So here's this physics book, and now I gave it a push, okay? Basically, the force of gravity still pulls it down, and the normal force still pushes it up. These two forces in the down direction and the up direction are balanced, okay? They balance each other out, or else the book would be like smashing through the table. But no force is present to balance the force of friction, because after you give it the push and you're not pushing it anymore, the book slides for a while but then eventually slows down. Okay, the force of friction is causing a acceleration. And remember, even though acceleration in normal terms is used to describe like speeding up, in physics it could be speeding up or slowing down. So this book is actually slowing down. So it says the friction between the table and the book surface exerts a leftward force upon the rightward moving book, and it slows it down. So I must have given it a push in the rightward direction, and sometimes they call that F applied or F app. And this force to the left is called the force of friction, which is usually FF or F sub F. Okay, and so it's unbalanced right now, and so the force of friction is slowing the book down, because after I give it the push, I'm no longer pushing anymore, and there's only three forces acting on the book: the gravitational force, the normal force, and the force of friction. Okay, and so it's unbalanced and it causes an acceleration. So to determine if the forces acting upon an object are balanced or unbalanced, you have to determine what forces are acting upon the object and in what direction. And that's going to lead us right into the next lesson. Okay? If two individual forces of equal magnitude and opposite in direction, so equal in numerical value but opposite in direction, that is said to be balanced. Okay, and that makes sense, I think. If you push on something to the right with, say, 10 newtons of force, and something else pushes on it on the left with 10 newtons of force, well, the forces balance each other out. Okay? The forces are unbalanced when an individual force is not being balanced by a force of equal magnitude and opposite in direction. So if I push on a box with 10 newtons of force and my friend on the other side pushes on the box with 5 newtons of force, well, I'm going to kind of like win the war, if you will. My force is not being balanced by my friend's force, and so the box would move, all right, because there's an unbalanced force. That takes care of this lesson. I'll see you guys in the next video.